Moment of inertia is designated by the letter I. This is for mass moment of inertia, and it is the resistance to motion of an object flipping around an axis. So resistance to angular motion. So just like for forces, we had sum of the forces equals mass times acceleration, and the bigger the mass is, the harder it is to accelerate. For angular motion, we have torque. Sum of the torques equals moment of inertia times angular acceleration. So it's just if you're trying to flip an object around an axis or spin it, something like that. Now, here, the forces always are summed, and this acceleration is center of mass. Now, torques can be summed around either center of mass or a fixed point. So there are two options for that. So just like we learned about yesterday for the fixed axis rotation, it could be summed around that fixed point or the center of mass. So for an example, if you have an object spinning around an axis like this, say its center of mass is here, call that C, and we'll call this O for the origin. Well, you can either sum the torques around center of mass or the origin. So either one is fine. Now you cannot sum them around here. Say this is the tip. The answer won't come out right. It has to be either the center of mass so that all the weight is equally balanced around that point, or the center of rotation. So it's got to be the center of something. Now, the way you get moment of inertia, it is the integral of distance squared over mass. So I equals the integral over m of r squared dm. So basically summing up every little particle on the whole body and its distance to get total moment of inertia. And r is this distance from the axis of rotation. So this also can be, if you don't exactly know mass, but you know volume, you can do integral over volume of r squared times density times dV. So you can calculate this. Please mute yourself. So you can calculate this either use an integral, or you can use CAD. Like if you have made something in CAD, a lot of times if you define the material, then it'll be able to calculate the moment of inertia for you. Or for simple shapes, you can look it up in a table. There's a table in the back of the book that has the mass moments of inertia. Be careful not to confuse this with area moment of inertia, which you learned about in statics. This is mass moment of inertia because it's resistance to motion. Something is moving, so it's the mass that has that resistance. So moment of inertia is a function of the origin and the axis, and it's always positive. Just like mass is always positive, and it is a scalar. So look at some common moments of inertia. And what their formulas are. So for a rod rotating around an axis at its end, so let's say we have a rod of length L and it's spinning around this axis, mass M, I equals 1/3 mL squared. Now, if instead the rod is rotating around its center axis, so let's say this is L/2, L/2, it's rotating around here, this moment of inertia equals 1/12 mL squared. So it's easier to spin something around the middle, kind of when it's balanced, than around the end when it's not. So this is a rod, or it could even be a flat rectangle, because it just anything that's skinny, and so that the length is a lot longer than how thick it is. So you notice L is the only dimension that shows up here. So some other ones. Now for a hoop, moment of inertia of the hoop, let's say this is R, and this is rotating around its center axis. So I for the hoop equals mR squared. Okay, because it's basically a sum of particles all around. So like particle here, particle here, particle here. It's just adding up all of those particles that are distance r away from the axis. So similarly, for just a particle of mass m, distance, say d away from the axis, then I equals m d squared. So the hoop is just a bunch of particles, all in a ring. So then for a disk, through its center axis, and say the disk is radius r and mass m, then moment of inertia for the disk equals 1/2 mR squared. Okay, so it's less than the hoop if it's the same m, because some of the mass is a lot closer to the axis of rotation, so it's easier. So it's kind of to average it out and makes it cut in half. Then finally, for a sphere, let's say here's the sphere. This rotating around an axis through its center, it has radius r. I for the sphere equals 2/5 mR squared. So these are mostly for something around, rotating around its center of mass, except for the particle, which is its center of mass. So that's rotating around a distance away. But you can see that when something is rotating around its center of mass versus when it's rotating around a different point, the moment of inertia changes. We can see that with the rod here. So say this is rod, hoop, disk, sphere, and point. Okay, now how do we know if, for example, how do we know what moment of inertia is if it's rotating around an axis that's not through the center? How could we figure that out? Well, there's a formula for it. It's called parallel axis theorem. Sometimes we abbreviate it PAT. So that is if an object is spinning around an axis that's parallel to its central axis, then the moment of inertia is also directly proportional to the distance between its central axis and the axis of rotation. So we'll draw out what that means. Say we've got object and center of mass is here. It could be rotating around an object that goes, an axis that goes through there. Or it could be rotating around an axis that's out here, distance d away. So for this axis of rotation, say this is axis C and this is the other axis, we'll call this one A. I around the axis equals I around the centroid plus md squared. So it's basically treating it as an object with centroidal inertia, but then it's removed to a distance where it looks like a particle. So it's just centroidal moment of inertia with, and then it's removed, so then you have the md squared from the particle. So you can find moment of inertia for any shape. Also, if you have an object that's got multiple shapes on it, then you just add up all the moment of inertias together. Now for composite bodies, moment of inertias add. So let's say you've got shape like this here. So you have this object and it's rotating around this axis. You just add up all the moments of inertia. So let's see, I for the circle, I for the triangle, I for the rectangle. So total I equals sum of all the individual i's, which equals sum of I for the rectangle plus I for the triangle plus I for the circle. So sum I for composite bodies. And finally, radius of gyration. So radius of gyration in the book, this is actually denoted as K, but they use like a little kappa kind of symbol instead of R. So it kind of looks like that. This is the equivalent distance to the center of mass, or like equivalent radius of an object. So if you have something with a really strange, like say some weird looking shape, and you end up calculating its moment of inertia. Say it has some moment of inertia I. Well, where is its like distributable radius? Probably going to be somewhere in here is kind of like the average. So once you find I, you can find its radius of gyration, and this is mk squared. So if you know moment of inertia, then you can get k equals the square root of moment of inertia over the mass. So this is just kind of an equivalent radius if you have something that's a weird shape.